Okay, so to kind of finish off chapter 11, we're just going to look at some properties of our power series. Some of these properties you're going to be familiar with because they're similar to how you worked with limits and derivatives and integration and everything else. Um, and we'll see how they are useful. First one is your sum and difference. So if you had two, sorry, series where say f of x comes out to equaling the summation of c to the n, x to the n, and g of x is another power series with a different coefficient, but notice they're both centered at 0, and they're both need to start. So, a couple things. They both need to be centered at the same location. So they're either both centered at 0 or they're both centered at the same a. So x minus 2 to the n, x minus 2 to the n. The other thing is their counter has to be the same. Their n starting value is both starting at 1 to infinity, not one of them starting at 1 and the other one is starting at 0. All right, so that all does have to be the same. The way their coefficients are determined could be different. One may be a more traditional Taylor, may be something else. But those pieces need to be the same. You can then just simply take n equaling 1 to infinity, and you can combine them into one series, right? And that's going to be equal to f of x plus or minus g of x, okay? Again, notice what must be the same about the series before you can combine them into one series. That's your first property. Your second property is multiplication. Not of two series. Be careful. Multiplication by a power. Multiplication by a power. So in other words, you've got your power series. We'll go from 0 to infinity, doesn't matter. Of c to the n, x to the n. Most basic power series centered at 0, whatever. If I go ahead and multiply that entire power series by, say, I don't know, here we'll put it in blue, x to the m power. All right, some other power. Maybe it's x to the third, x to the fourth, x to the fifth. Okay, you can go ahead and distribute it inside the series by doing m plus n. Sorry, you hear barking in the background. Some craziness going on. So in other words, if you have x to the third, then this becomes x to the n plus 3. All right, so that's another thing you can do with your series. Hopefully you won't hear that barking too badly. The last one, and one of the most important, is a composition. This one right here, by the way, if you're going on to differential equations, I think you'll end up using that a lot in differential equations, but not so much. Just showing it to you now. This composition one has a cool, really allows us to do some pretty nice things. All right. So let's suppose we have a function, we'll call it h to the n, and it's some type of series, right? The summation means you can also plug it into the function. Yeah, this one's gonna you're gonna understand much better when I show you an example. So we'll come back to this one in a minute. All right, let's look at some examples. Like I said, this third one's going to really come in handy with like integration and stuff like that. All right, so the first property we did, let's suppose I had from 0 to infinity n plus 6 x to the n, and I'm going to add that to another series. So I'm going to add these two series together. Again, what are you noticing? This is the same. The counter is the same. That's what must be the same. The powers on the x and the counter below the summation have to be the same in order to add or subtract. So that means you can combine these into one series. All right, we can do this. N plus 6, x to the n, plus n, x to the n. All right, and then we can also do this, n plus 6 plus n, x to the n, which of course would give us all right, so you can actually add series together. Again, as long as those two conditions hold, the counter starts the same, and it's the same x and same power. Okay? All right. That second one we looked at, if I want to take an x squared and multiply it by this series, I can do that by bringing it into the summation, which would then give me so that one is kind of it's basically the distributive property, right? So in other words, if you had an x squared times x plus 2x squared plus 3x cubed plus dot dot dot, right? That's just going to give you x cubed plus 2x to the 4th x to the 5th plus dot dot dot. And then if you go ahead and work this out, you'll see, oh, what do you get? When it's 1, you get your x cubed. When it's 2, you get your 2x to the 4th and then your 3x to the 5th, dot, dot, dot. So you can see that they both come out the same. Now, as I said, this one is one of the most important ones. What you should be doing is memorize some of the classic ones, the classic Taylor polynomials that we set up. So one of the ones we set up, we did in the first video, was sine of x, right? We know sine of x equals this. This is a Maclaurin centered around 0, so it's a Taylor polynomial centered at 0. We worked out this series. You should know this one. You should know cosine x, e to the x. Another one you will want to work out to kind of memorize, and if it's in the PowerPoint notes in this section as well, and I'll let you figure that one out on your own, is ln x plus 1. I mentioned it in the first video. I don't think we worked it out, but ln x plus 1, also notice you can't do a power series on ln x because there's no 0. You can't center it at 0. That's the problem with ln x by itself. ln x we can't do a Taylor polynomial estimate for because we can't center it at 0, but we can do it for ln of x plus 1. We just have to shift it. You look through those PowerPoint notes for chapter 11, you will see a bunch of them. These are the ones you really should just have memorized. There's other Taylor polynomials for like tan inverse and some other functions, but this one's pretty common. This one, cosine e to the x, you got to know these. All right, so how's that helpful? Yeah. What if I asked you to find the integral of sine x squared? So, think about that. Not sine squared x. Please note, this is not, which is this. Okay? Not that. So you're not applying your identities for sine squared x. That's not going to help you. I want sine of x squared. Can't do a u sub because you don't have the derivative of x squared, so you can't let u equal x squared because you need 2x. You can't introduce a 2x. You can try integration by parts, not going to work. Trust me. If you let u equal sine x squared, dv equal dx, yeah, you're just going to get caught in a loop. It's not going to work. So here's where your power series is going to come in handy. Because, well, wait a minute. We can write sine x squared as a power series using composition, where our h of x is our x squared term. In other words, you know what sine x looks like. It's right here in red. Write it as a Taylor polynomial, Maclaurin actually, because it's centered at 0, of sine x squared. We're just going to use composition, right? Sine x squared. Well, my x now becomes x squared. So my second term is x cubed over 3 factorial x to the 5th over 5 factorial. And you're just going to put in x squared to all those terms. Right? So what does sine x squared look like as a Taylor polynomial? Sorry about that. That is a 6. Let's work it out. Let's work out the 3 factorial too, which happens to be 6. X squared to the 5th is x to the 10th. 5 factorial is 120. Yeah, well, you can, here, let's get, you can calculate what 7 factorial is. I just don't happen to have it in my calculator on me. You have to do 7 times 6 times 5 times 4 times 3 times 2, and so on. Okay? Why is that helpful? Because now I can take the integral of this. And I can at least get an estimate. All right? Because you can integrate x squared, you're going to have x cubed over 3, x to the 7th over 7 times 6. We'll just do a couple terms. X to the 11th over 11 times 120. What's that? 11320 maybe? I don't know. It's 11 times 120, and so on and so on and so on. So you get the idea. This is where Taylor polynomials become really useful in such fields as electrical engineering and different things. We're having to get these integrals of the wave functions. So there is application. And it works with derivatives as well. Here's another thing I want you to think about when dealing with a derivative. Let's just do a basic. You can take the derivative of the function without expanding it by applying the rules of derivatives, right? How do you take a derivative? Well, you take the n, you multiply it out front, so it does not become summation of n times c to the n x to the n minus 1, just by basic rules of derivatives. Now, be careful. Here's where you need to be careful when doing that, because f of x itself is going to look like c to the 1, or 0, sorry, start this at 0. I don't know why I put 1 there, I meant to put 0. Right, x to the 0, which goes to 1, plus 0, 1, x to the 1, 2x squared, right? What happens when you take the derivative of this expanded series? First term goes away, and you're just left with c to the 1, right? Do you see that? So you have to make sure the derivative gets you that. So here's my question. Can I get that by starting, I'll put this in red. Hold on. Whoops, I meant to erase it. Can I get that by starting at n equals 0? Well, if I start at n equals 0, no, I'm going to get 0. Do you see that? When you take a derivative of the series before the expansion, you have to shift the counter, because we need that first term, that c sub 0 term, to go away. You need to start at 1. If you start at 1, then you will get this function. Same for the next one. We can take the second derivative of this series itself, right? You now have n times n minus 1, c to the n, x to the n minus 2. But here's the difference. You now need to start at n equaling 2, and then this will generate double prime. That goes away. The rest of the terms. Not something you're going to use in this class. This is more of a helpful hint for those of you going on to differential equations eventually. Okay? All right, so that kind of wraps up our overview of Chapter 11. Like I said, it wasn't hitting everything in Chapter 11. You'll notice when you get to Math Lab, some of the problems are like already done and you got credit for, because there was stuff I decided we were taking out of Chapter 11, so don't worry about it. There's a lot less Math Lab problems than are actually listed, which should make you pretty happy when you're doing them. So please, don't think it's too daunting and don't try it. The Math Lab is much less than what it seems like, because I've kind of gotten rid of some of the, like we skimmed over, we really didn't get into error. It's incredibly tedious and not really necessary. So I got rid of a lot of those problems and some other problems as well. So again, that wraps up Chapter 11.